We will move on to our next speaker. And again, apologies if I mispronounce your name, which I suspect I will. Tuong Vu, hope that wasn't too bad. And he's going to be talking to us about challenges of 3 objective bi-level model discovery, application to alcohol use in New York State from 1985 to 2015. So please take it away.
Hi guys, you see my screen okay?
Yep, sure do.
Yeah, right. Okay, here's the title of talk. So we are a team from Sheffield, UK. And my name is Tuong Vu. Yep, so the pronunciation is fine. So the agenda of my talk today is first, I'm gonna go really briefly about the Cascade project. So we try to do mechanism-based theory-routed agent-based simulation. And then I'm gonna talk about how do we do that in alcohol use context, the model discovery process, the result of that, and the conclusion. So Cascade project, we are funded by National Institute of Health, and we try to explaining the long-term trends in alcohol use, liver cirrhosis, and alcohol poisoning in the US from 1980 to the present. So when we look at explaining alcohol use, we found out that there are 4 source theory that can do this: Rome theory, behavioral economic norm theory, and contagion theory. But we have some challenges while we try to comparison and integration this theory into the models. So there's no common ontology of concept between the theory. There's no library. There's no standards for iteration. Also, there is no computational machinery to perform this kind of task. So what we do is that we build some. And we published the MBSSM software architecture and as well the conceptual models in a JAS paper in 2020. What we wanted is a meta theory that could describe a wide class of social theory. We found Hestrom analytical sociology, Coleman both, Archer morphogenesis. And what we did is that we combine all of this together to create a general macro scheme. And it actually based on the common both, right? You have micro level, macro level, and then you have a series of mechanisms that connect them between social entity and micro entity. And then we also allow a macro to macro mechanism in this case because some theories supported this. So we allow it in our general macro scheme, but you can use it or not, if up to you. And then we build a software architecture for that. We published it in on the online repo, and then we also developed some tutorial for it. And here's the website for that. So now let's talk about agent-based modeling for alcohol use. So for this case study, what the phenomenon we're interested in is the trends of alcohol use in the New York State from 1985 to 2015. And then we noticed that there's a decline in consumption in the late 80s and early 90s and reversal back. So to explain this, we use a theory we decided to use here is social norm theory combined with the dual process theory of region action and habitual behavior. But so when we try to do it, we have some issues. Well, that's when we do parameter calibration, we cannot reproduce both male and female trends of drinking simultaneously. So if you got really good male, the female is really bad. If you got good female trends, then the drinking behavior in the male is really bad. So what we do is that we perform a model discovery by diagnosis of structural differences. The methodology we use is RAMA-based genetic programming. So we use RAMA to guide the search process. And we have 3 objectives. We try to replicate male and female drinking behavior by comparing simulated data to the real data. And also we try to minimize the complexity of the whole process of the structure. So if it's too complex, you cannot explain it. And in this particular case study, we perform a bi-level optimization by including the parameter in the rammer. So now we will try to modify both structure and the rammer at the same time. So now it's here the target data from the New York State. So we got this from the IGSSS survey. There are 6 targets. On the left is male, on the right hand side is female, and then you have prevalence of drinking, frequency of drinking, and quantity of drinking. And you see that if you look at frequency here between 1890 to 2000, you see that there's a drop and then come back, and the same here, drop and come back. Okay, so in order for this to work, we need a micro simulation, which is a synthetic population of agents with realistic variable of demographic, alcohol use, behavior, and we generate one using multiple data sources, and our agent is updated over time for age, social roles, and household income. So now let's talk about the norm theory and how we apply it in the alcohol use modeling. So for norm theory, there are 2 concepts. In this case, injunctive norm and descriptive norm. Injunctive norm is what society sees as acceptable behavior, and descriptive norm is the norm is like actually how people are drinking. So for injunctive norm, for example, say if you're pregnant, you're not supposed to drink, for example. And the descriptive norm is the drinking behavior you observe of people around you. And in the norm theory, if you look at the macro level, so there's two transformation norm mechanism I want to discuss here. First is about the relaxation, which is in blue. So people drinking behavior will change the norm over time. Basically, it relaxes the norm. For example, like over time, it's more acceptable for you, for let's say for female to drink. That is the relaxation of the norm. And then there's another mechanism here is the punishment, the tighten of the norm. So if drinking causes social disorder, that will be less acceptable to do drinking. So the injunctive norm going to be tightened. And then mapping all of that from the norm theory into the MBSSM architecture, we have in a situational mechanism, we have an update of the perceived norm where the individual look at the norm from the macro level, and then they have their own perceived norm because, for example, for me, people the same sex and age group will have more influence to me rather than people that, let's say, much older or a different sex will have less influence. And then from that, we have a number of rings when you do action mechanisms. And then transformational mechanism already explaining where individual behavior will change the norm over time. So now let's look at action mechanism and situational mechanism. So how individual making a decision. So from the norm, from the identity. So in our models, individual have an identity of based on sex and age group. You perceive the norm, and then you have your desire to drink, basically your history, your behavior, your habit of drinking. And then these 2, norm and desire to drink, going to be weighted by autonomy. So you can think of autonomy is that if you have high autonomy, you will you can ignore the norm and then you just follow your desire. But if you have low autonomy, you would try to follow the norm more. Okay, so that all the mechanisms, and in our models, in order to map different theory into the agents, we design a dual process for agent decision making. So every time take the agent, we have to follow either pathway, habit pathway or intention pathway. So habit pathway is on the left hand side here. So if they go to habit pathway, they just follow their drinking history. And then if a person is go to intention pathway, there are a series of equations that calculate attitude, norm, perceived behavior control to calculate the intention of that agent, how much to drink. and then you sample a number of rings from that. And the decision to what happened between habit and intention is decided by automaticity. So if you have high automaticity, you go to your habit more. And then if you have low automaticity, then you have to make a lot of, you go to intention pathway more, so make a lot of intention. And now we're mapping the social norm concept into this this attitude norm in PBC. We see that attitude will be mapped, the desired to ring into it. And for the norm, we're mapping the injunctive norm and descriptive norm. And in these particular models, we don't have perceived behavior control. So this is the, oh, sorry, I have an updated slide. So this one is not the updated one, but the equation is not looking good. But basically the attitude is if a human moral design is, the attitude is the multiplier of autonomy and desire to ring. And the norm is the multiplier of 1 minus autonomy and the average of the two norm. And then it goes to this log-odd equation with the beta attitude multiplied with log-odd attitude, beta norm multiplied with log-odd norm. And then we just, like logit model, you say e to the power of log-odd divided by the sum of everything to have intention probability. And then the agent make decision on that. So now what we try to do is that we try to, using the GP process to modify this equation, particularly the first log-odd attitude and log-odd norm, to see what are the structure that we can come up with. Before that, we just do a quick parameter calibration, just calibrate the sig target by comparing the model output to the target mean. So this is can be used at the base models, and we can look at it as a comparison later if you want as well. So for the model discovery method, the process is that first we design models. So in step 0 and 1, we design a model. In step 2 is that we talk with the human expert, and then we come back to step 1 to improve the model again. Step 4 is we actually decide, okay, what is the primitive, what is the rammer that we're going to use for the search process. The calibration is step 4. Step 5 is we start the search by randomly generated a population. And then step 6 is just the evolution process. And then step 7 and 8 is that we are looking at the structure, the new structure come out from the GP and see whether it's credible. And we see whether we can discover any new knowledge from it. So here's the rammer. We can go through this together slowly. It's quite complex. So so each of the structure, we have mutable element to it. So it's the P. We're going to give a program. So the first element is log-odd attitude. And the expression we allow it to be is that it can be either log-odd design or autonomy multiplied with the design. And then this is like we split it into 2 levels like this, so that if you go to this level, you introduce more autonomy term, so it get more complex. So you get more knot basically. Right. So for the norms, we allow for the expression we allow the weighted sum of 2 variables by a constant. We allow a variable to be there. We allow 1 minus autonomy multiply with the sum or multiply with the variable. And the variable option we allow is injunctive norm and descriptive norm. So this is in line with what we just discussed about attitude and norm and how we're mapping this concept into this dual process theory. Okay, and now we try to include the parameter in the rammer as well. So for the beta attitude and beta norm, it can be a constant. So C can go from 0.0 to 1 with a step of 0.01. And also this C also you use in the weighted sum function as well. Finally, for the automaticity, you see that is decided which pathway you go. So we have 6 options, and then I plot for the first 4 options here. So if automaticity is left, your distribution skew to the left. So for example, this one, you have 20% of the time the agent will do we do habit, and then 80% they will do intention pathway, and then so on. And this automaticity here is different. So each of the agent will just pick an automaticity from this distribution based on their drinking level. So low drinker drink I think one drink per month in general, and then high drinker have like more than like 5 or 6 drinks on average, and then medium drinker is like somewhat in the middle. And then we have extra 2 options here. Zero is that everyone is automatically 0, so it means that everyone will do intention. And then one means that everyone will do habit, we follow the history. And then we have also an extra conditions that the logout attitude need to contain at least one design term, and norm must contain at least one injunctive norm or descriptive norm. So this design is to avoid the cases where logout attitude can be equal to a constant, for example. Okay, so that's the RAMA is done. Take a while. So now let's, how do we set up the model discovery process? We use a software named PonyG2. And then we have 3 objectives as discussed. We do 500 candidates for 50 generation. And then we also carry forward 10 best candidates for each generation. And this process is expensive. It took 16 hours for us to do it with 36 cores. And if you look, so now we look at how the performance of the GP. So if you know about it, this concept called hypervolume, which means that if you look at a reference point, this structure, each of the point is a structure, and at first it will be you have a Pareto front here, and it's going to move away from the reference point. So this hypervolume in yellow is going to increase over time. So if we're looking at this, we see that the algorithm, the process actually converge, and it worked well. So looking at the Pareto front, in the last generation, the 50, we have 44 structure. So because we have 3 objectives, so I plotted in 3D. You have fitness of male here, X, fitness of female is Y, and then the complexity is Z. And then here is like I map the 3D into a 2D graph. And you see that they have a trade-off between male and female. And then if you want to increase, if you want to have better fitness for male and female, you go over this area. In order to do that, the size is going to be bigger, right? The size, it become from dark to a lighter blue. So light blue mean like bigger size, it's more complex. The complexity increase. So the trade-off in terms of complexity versus the 2 fitness as well. Okay, so now let's look at some time series of the result out of the 44 structure to see what we learn from it. So this is the first one that I try to find the best for all 3 fitness. And you see that the intention is driven by injunctive norm because we have attitude design. Norm is injunctive norm, but if you look at the weighting here, it's the beta for the norm is much bigger than the attitude. And for the automaticity, for the medium and low drinker is habitual because 1 and right mean that you skew more to the right, you do habit more, and then for high drinker is bimodal. And now if we looking at best for male and female, so we remove the complexity term, right? So in order to do that, the structure use 1 minus autonomy in the norm here. So it increases the complexity for a better male and female fitness. And again, the injunctive is still driven by the norm when you look at the beta, and automaticity is the same. So now let's look at the best male. Now we have the same for the attitude and the norm. And then looking at this, you have the better fit for male quantity, but the validation period is not as good, right? You see it's going off here. It didn't go up, it just go like straight line. and intention and automaticity is the same. And here is the second best male. So that you see, if you compare with the best one and the second best, it include the frequency is just slightly better. But like if you look at the log-odd norm equation, it's very similar to the design by human, where it involves both injunctive norm and descriptive norm in this case. Now let's look at the best female, right? Because previously, if you look, you see that the female not doing really well. And now for the best female, it worked well, but trade-off is that the quantity of the male is not as good. But in this case, you see that the intention is driven by both attitude and norm, right? So 0.6 and 1. In the previous one, attitude is really low. And all of the automaticity now is habitual, it's skewed to the right-hand side. So now we look at the second best. It's the same as previously, but you see that there's a slightly different in the low drinker here. So low drinker here, the best is right, the second best is left. So now you may not think, oh, maybe the automaticity of low drinker is not that important, right? Maybe only these two matter. Okay, so we've got look at all the previously. You see that there's always trade-off. You got a good male, female is not as good. Here you get better female, but like each trade-off is the male not as good. So now I try to find like the best one that can actually replicate the phenomena of the decline consumption and reversal. And this is the one that I find. Log-odd attitude is design, and the norm is just injunctive norm. Intention is driven by both attitude and norm. And then you have this set of automaticity. Interestingly, this model is the ranking. When you look at the finish of male and female, it's 27. So it's not the top, but the trend is really good, right? If you look at the trending, it's really good. So the observation is we see here that if you look at the plot, there's always a trade-off between the three fitness. If you go, it's really hard to get both low male and low female. And I think the compromise way to do is that medium male, medium female, and low complexity is a good compromise in this case. And then I look at all the structure and actually can replicate the phenomena we want. And I found they have the same log-odd attitude and log-odd norms. And the intention is driven by both. If you look at the beta attitude and beta norm, they are similar. And they're quite balanced. And the automaticity of the medium drinkers is always high, either one or right. So we just draw some insight from this is that there are key similarity and difference between male and female agent structure. Intention play a role in high drinking male, but low drinking female. Habitual drinking dominate the medium drinking male and female. For intention pathway, injunctive norm are important, but they're more important for males. And for intentional pathway, moderation of the norm by autonomy is important for males, but unimportant for females. So in conclusion, this demonstrated we can explore both structure and parameters simultaneously. The rammer can help you to capture and encode the social ontology from domain experts. But there's a lot of challenges, like how you balance in the way the trade-off between different targets. You can include a parameter, but our suggestion is that you need to minimize them so that the parameter search not overwhelming the structural search, because what we're aiming for here is the structural, not parameter. And also beware of overfitting. You see that the other one not fit, not the best fit, but the trend is really good. And theoretical interpretability is always difficult. Yeah, and this is the end of my presentation. Thank you.
Thank you. That was really interesting. We do have time for a couple of questions. If we have any, you can put them in the chat or raise your hand and let me know. Well, I had one question.
Go ahead.
Oh, all right, real quick. And I'm sure you already said this, and I just managed to miss it.
No, please go ahead.
Okay. your male and female agents, were you trying to have one decision rule across both, or could they be heterogeneous?
We have one decision rule across both, but they
Okay.
the difference here is in the parameter and in their own. So the automaticity can be different, for example, but for the
Okay.
decision rule, they're the same. Yeah.
Okay. Okay, Josh, please.
I was just going to clarify something. Tuong, great talk. Of course, it's great work. Just to hark back to a point that was made earlier. I mean, in this case, there was a human domain. There was a human model that that was included. But just to be clear, it was the model of a particular human. It's not the consensus model of some community or anything like that. But we thought it would be interesting to start with, what one of our leading thinkers thought was an appropriate starting point, and it turns out to be very far from the Pareto frontier. But nonetheless, it's an example of something we talked about earlier. But yeah.
Okay, we've got a couple of questions in the chat. I think they're somewhat related, so I'm going to ask them both at once, and then we can tackle them. So by increasing the complexity of the structure, would it be expected for the fitness of both male and female to improve in general? And then the other question, which I believe is related, how do you assess overfitting? And the second question, if you had more flexibility in the grammar and more optimization power, do you think you could find even better solutions on all three axes?
Yes. So we actually before this we actually have some iteration where we use a very complex grammar which allow a lot of flexibility, and yes, we can find better fit in all of the the targets that we're aiming for, all of the three targets. But the problem is that with that much flexibility, it creates a structure that's too complex for interpretation. So we look at it and then we try so many things, but we don't understand what's happening anymore. So in later iteration, what we did is that we actually introduced a more restrictive grammar that say, okay, you can only do this, you can only use this element. In the previous grammar, we allow like multiplication minus of everything, and it's we cannot explain it anymore, even that the fit is right. So that's the trade-off there for you, like better fit but lower interpretability.
Fascinating.
Yeah, and for the overfitting, I think it's tough, right? I think we can change the Finnish equation, trying to have a term to address the overfitting, but we haven't do that yet. In this case, we just eyeballing, looking at the time series, and see what's happening. Yeah, basically.
Okay, Elizabeth, final question.
Yes, can you hear me?
Yep.
So this is great and really interesting work, but I'm kind of wondering, it's kind of a very high level question, but so you found that the model did not fit as what, if you could get it to fit well for males, then you couldn't get as good a fit for females. And it seemed, based on, at least, and I may be misunderstanding, you're looking for a model that's going to give a good fit for both simultaneously. However, I thought it was really interesting that it didn't, you could get a good fit for one and not a good fit for the other. And so what do your domain experts say about maybe a very different understanding or reaction to norms between men and women? Like maybe that not fitting one or the other is a really interesting and important finding, and it's not so important for the model to fit both.
Yes. So like that's the thing. We're looking at the data. Like we see that they're definitely different in male and female, and then we try to build the models. I think over time we try to separate them more and more. So in our parameter, we always try to separate male and female more and more and more and more. So like we say, oh, this didn't work out. Let's let's separate the automaticity by male and female, for example, instead of low and high, of just by their drinking level. So I think that's one way you can do it, or even more, you can go to the stream and introduce different behavior rule for male and female, and I think sometimes that makes sense.
It seems like your model may have uncovered something interesting and in the data that's quantifiable, right? As opposed to sort of the qualitative way that a social scientist might look at it, you can actually quantify the differences between male and female behavior as they relate to your encoding of norms.
Yeah.
Anyway, it was just really interesting.
Okay.
Yeah.
Okay, thank you, everyone. That was fantastic. Now we're going to move into